Okay, so this is our next video on derivatives for Math 1560 Calculus 1 at U of L for fall 2017. And we're going to cover a couple of the basic rules for derivatives in this video, namely the sum rule and the constant rule. So let's start with the sum rule. So the sum rule says that if you want to take the derivative of a sum, it's the sum of the derivatives, okay? Not so surprising, right? We know the same sort of rule applies with limits. Limit of a sum is the sum of the limits, and the same thing is true for derivatives. The derivative of a sum is the sum of the derivatives, right? If you want to sort of state this in Leibniz notation, we could say like this: the derivative of f of x plus g of x is f prime of x plus g prime of x. Okay. So what the sum rule says is that, and of course you can extend this from 2 to any number of functions using the fact that you can always group things, right? By associativity, you can group things together. You can extend this from the derivative of 2 things to 3 things to 4 things to however many things you want to deal with. And what the sum rule says is that whenever you need to take the derivative of a sum of functions, you can take the derivative term by term. So you just differentiate each function in the sum individually and you get your answer. And so that's how this works. So for example, if I wanted to take the derivative of, so now we know a few powers. We'll say maybe we have like x to the 5th minus x to the 7th plus the square root of x. And it works just as well for subtraction as it does for addition. We'll do the proof for addition here, but we'll see that subtraction works just as well. So how do we deal with this? Well, first of all, remember that the square root of x is x to the 1/2. So if we take the derivative of this, we can apply the power rule to each term individually. We get 5x to the 4th minus 7x to the 6th plus 1/2 x to the, so subtracting 1 from 1/2 leaves me with minus 1/2. Okay, so that takes care of the derivative of a sum. All right, so how do we see that this is true? How do we prove this theorem? Well, we can look at the definition of the derivative, and the definition says that the limit as h goes to 0 of, so what am I doing? It's going to be this. It's going to be f at, so if we're taking the derivative at a, f at a plus h plus g, evaluated at a plus h. Okay, there's our function evaluated at a plus h minus f of a plus g of a, okay, over h. That's what we get when we just plug things into the definition. But you can see that it's easy to rearrange this. We can push this minus sign through, and of course that minus sign applies to both, and so we've got f minus, so f at a plus h minus f of a. We're going to group those together, and then we've got g at a plus h minus g of a, and we're going to group those together, and we can divide each one individually by that h on the bottom, and that's going to give me this. It's going to give me f at a plus h minus f of a over h. And then, and of course, I can take the limit term by term as well, so I can break it up like this. The limit g at a plus h minus g at a over h. And we see that that's exactly f prime of a plus g prime of a by the definition of the derivative. Okay, now the constant rule says that you can pull constants out of derivatives. So in the Leibniz notation, it says if I want to take the derivative of a constant times a function, that's the same thing as the constant times the derivative of the function, right? So just as with limits, if there's a constant inside, you can bring it out front, okay? And so as a quick example, well, in fact, now what we can do is we can combine the constant rule with the sum rule, right? And we can say things like, okay, let's say I want to take the derivative of, say, 3x squared plus 6x plus, I don't know, 2. Well, we can take the derivative term by term, and we can also pull out the constants. So we can write it like this, plus the derivative of, we'll just leave that last one as the derivative of 2. And so now we get 3 times 2x, and oops, that was supposed to be an x. I got a little bit ahead of myself there. Derivative of x is 1. That's where that 1 came from. The derivative of any constant, you've probably seen that the derivative of any constant is 0. That's also easy to see from the definition. I'll leave that as an easy exercise for you guys to try out. And again, if we wanted to kind of see why the constant rule works, you can probably see what's going to happen here, right? So we get c times f at a plus h minus c times f at a over h. And well, that constant, you've got a common constant multiple there, so you can factor it out, right? You can write this as the limit h going to 0 of c times f at a plus h minus f at a over h. And then we know that one of the limit properties is that we can bring any constant out of the limit. So if we bring that constant out, I'm going to skip that step because we're out of room, but if I take that constant out, what am I left over with? I'm left with the definition of the derivative at a. Okay, so those are the sum and the constant rules. They let us handle, simple derivatives. In particular, notice that we can take care of the derivative of any polynomial now. In the next video, we're going to look at the product rule, which is more complicated than you might think.